This presentation is part of a lecture series on multi-resolution signal and geometry processing by Michael Adams at the University of Victoria in Victoria, Canada. For those of you who might be interested, a copy of the slides for this lecture series, as well as the corresponding textbook, can be downloaded from the website whose URL is given on this slide, in particular this URL here. In this section of the lecture slides, we're going to look at some example programs that make use of the CGAL library. One example of a simple program utilizing the CGAL library is the meshMake program, introduced on this slide. This program simply generates a triangle mesh that corresponds to a tetrahedron. So first it uses the polyhedron 3 class to construct a polygon mesh that's associated with the tetrahedron. Then it writes this mesh to standard output in OFF format, in other words, object file format. Now I'm going to give a walkthrough of the source code for the meshMake program. This program consists of a single source code file called meshMake.cpp, and this is the file that we're looking at now in my editor. So from line 6 to line 10 we have a number of include directives. The first one is just for the standard library header file IO stream. The next 4 include directives are for files that are header files that are part of the CGAL library, these 4 files here. Simple Cartesian has stuff related to the simple Cartesian geometry kernel that we're going to be using in this program. Polyhedron 3 has the stuff for polyhedron 3, the polyhedron 3 class that represents polygon meshes. And then the other 2 remaining header files have some other helper code that's related to polyhedron 3 that we need to include. The first of these is for being able to do I/O, reading and writing polygon meshes in various formats. And polyhedron incremental builder 3 is for functionality for incrementally building a polygon mesh. And the next thing we have is a bunch of type defs, just for convenience and to avoid having to type out really long type names repeatedly. So we define a real type which corresponds to double. Then we specify a type called kernel, which corresponds to the geometry kernel in CGAL that we're going to use. And in this particular program, we're going to use the geometry kernel simple Cartesian with real plugged into it. This corresponds to the type that's used to represent coordinates. So coordinates are going to be represented with doubles, since real has been aliased to the type double. The next type that we define is called polyhedron is simply a short form for our polyhedron 3 that we're going to be using here. And polyhedron 3 takes as a parameter the kernel that we're using, which is basically the type from the previous line. And then we have another type which represents the half-edge data structure that's used by the polyhedron class that we're using. Then on line 19, starting on line 19, we have a functor class called meshBuilder, and this class is used to incrementally build up our polygon mesh that we want to build. Basically, we're going to build a polygon mesh that corresponds to a tetrahedron. So there's 4 triangle faces that we need to construct and link together in the appropriate way. So being a functor class, this class doesn't provide too many members. It has a constructor and then overloads operator round brackets, the function call operator, because it's a functor. And this functor is the thing that actually builds up the mesh. So if we look at what's happening inside this function, we create some type aliases just to save some typing. So vertex refers to the vertex type associated with our half-edge data structure, and point corresponds to the type that's used to represent coordinates of vertices. And this particular operator around brackets is passed a half-edge data structure. This is the half-edge data structure that's associated with our polygon mesh. Again, CGAL uses a half-edge data structure to represent polygon meshes when you're using the polyhedron 3 class. So this is the half-edge data structure that we need to update as we're incrementally building up the mesh. So the first thing we do is we start out by clearing out the half-edge data structure so that there's no vertices, edges, or faces. We start with an empty mesh. Then we create a polyhedron incremental builder 3 object. And the constructor for this type, it takes 2 parameters. The first is the half-edge data structure for the mesh that we want to incrementally build. And the second parameter is just a Boolean parameter, true or false, which indicates whether or not error messages should be printed to standard error. So true enables the printing of error messages, false disables them. So in this case, if there's any errors that occur while the mesh is being built up, error messages will be printed to the standard error stream. Then the next thing we do is we specify, we call the begin member function, or sorry, begin surface function, member function, of the incremental builder class, this object B, and we specify the number of vertices and faces in the mesh that we're about to construct. So this is, since this is a tetrahedron we're trying to construct, there's 4 vertices and 4 faces. Then the next thing we do is we specify the vertices, each of the vertices of the mesh, by calling the add vertex member function. And these vertices will be numbered from 0. Each vertex will be assigned an index. So the very first one that we add will have the index 0. The next one that we will add will have index 1, and then index 2, and then index 3. And these indexes we'll use later when we're trying to define the faces for the mesh. So this will essentially introduce a vertex with index 0 with coordinates 1, 1, 1, a vertex with index 1 which has coordinates -1, 1, 1, and so on for the remaining two vertices that we have here. So that basically adds the vertices to the mesh. Now we need to actually add the faces. And the proper geometric term or proper geometry term for the face is actually a facet. But often people just say faces. But technically vertices and edges are also lower dimensional faces. Facet is the highest dimensional face. So first, to create a new face, we call begin facet. And then when we're done defining our new face, we call end facet. And in between begin facet and end facet, we call a whole bunch of add vertex to facet function calls. And each of these function calls is going to add a new vertex to the face. And since these faces are triangles, we're going to need to add 3 vertices. And the numbers that are passed here are the corresponding indexes for the vertices. So this value here, 0, corresponds to the vertex with index 0. And then this index 1 corresponds to the vertex with index 1. And this index 2 here corresponds to the vertex with index 2. So these are the 3 vertices that are comprising this face. And the vertices are specified in counterclockwise order. So this would be this is going to define, these lines here will define one of the 4 faces of our tetrahedron. Then we proceed on for the remaining 3 faces of the tetrahedron. The structure is very similar. We call it begin facet. Then we have 3 calls to add vertex to facet in order to add the 3 vertices of the face. Then we call end facet. And then this process repeats for the 2 remaining faces, this face here, and then this face here. And then at the very end, we have to call the member function end surface to say that we're done defining this polygon mesh. And then our function simply returns. So this is our functor class. And then if we proceed on to look at the main function, what it's doing, it's actually quite short. The first thing we do is we create a polygon mesh, one of these polyhedron types, which is called mesh, and it's default constructed, so this will generate a mesh with no vertices, edges, and faces. It's empty. Then we construct a mesh builder object. Here's type mesh builder, which we define up above. The object's called mesh builder, and this is the functor object that's going to, or functor, which is going to be used to do the construction of the mesh. Then what we do next is we invoke the delegate member function of our polygon mesh. This mesh is currently empty. We're going to invoke the delegate member function, and what this does is this delegate member function is going to call the operator around brackets and invoke the function call operator for this mesh builder functor. So essentially it's going to call the operator around brackets that we were looking at up above for the mesh builder class, and this is going to have the effect of constructing incrementally our mesh. And then after this function returns, our mesh will be created. This mesh object will now actually be the tetrahedron mesh that we've created. And then in the last step, we just output our mesh to standard output using the stream inserter, which is overloaded by the CGAL library, so it does what you would expect. It writes the output in OFF format to standard output. And then we just have to make sure that there were no errors that occurred. If there is, we're going to exit the program with an exit status of 1. Otherwise, we exit with an exit status of 0. Another simple example of a program utilizing the CGAL library is the meshInfo program. This program extracts and prints some basic information about a polygon mesh. So the program begins by reading from standard input a polygon mesh in OFF format, in other words, object file format. Then various information is extracted from the mesh, including the type of mesh, in other words, the type of faces in the mesh, whether it's a triangle mesh or quadrilateral mesh or some other scenario. The number of vertices, edges, faces, and half edges in the mesh, the minimum, maximum, and average valence of vertices in the mesh, and the number of non-planar faces in the mesh. And all of the above information is printed to standard output. Now I'm going to give a walkthrough of the source code for the meshInfo program. This program consists of a single source code file called meshInfo.cpp, and this is the file that we're looking at right now in my editor. So to begin with, we have a bunch of include directives. The first two include directives are for just standard library header files, so they're not very interesting. The next four include directives are for header files in the CGAL library. The first two are necessary for the geometry kernel that we're going to be using later, which is the filtered kernel with Cartesian plugged into it. Filtered kernel is a template class. The next two header files, polyhedron 3 and polyhedron IO stream, these are for various aspects of the polyhedron 3 class. Polyhedron 3.h has the actual type definition for polyhedron 3, and polyhedron IO stream has the necessary declarations and definitions related to doing I/O for the polyhedron 3 class, so being able to read and write polyhedron 3s in, for example, OFF format. Then the next few lines here are for introducing some type aliases just to make the code a little bit less verbose. So to begin with, we introduce a real number type called real, which corresponds to the type double. Then we define a type for not quite the kernel we want to use, but a kernel which is related to the kernel that we want to use, which is CGAL Cartesian with real plugged into it as a template parameter. So this is going to be a geometry kernel where the coordinates are represented with real values, where real corresponds to double. But this is not actually the kernel we want to use. We want to actually use a kernel that has exact predicates, and this particular kernel doesn't have exact predicates. So what we can do is we can plug this kernel into the filtered kernel template class in CGAL. And what this does is it takes a kernel, for example, kernel 0, and from it constructs a kernel which has exact predicates. In other words, predicates that give the correct answer in spite of round-off error and so on. And this is the kernel that we're actually going to use. So we give this name, or this type, the name kernel, which we use later on. And then we created a type alias for the polyhedron 3 class with our particular kernel that we want to use plugged in and call this polyhedron. And then we create a type alias for point, which is the point type associated with the kernel that we're using. Then if we move on to the main function on line 20, this is where the real work actually begins. So the first thing that we do is we create a mesh object. Polyhedron is our polyhedron 3 type. We create a mesh using the default constructor, which will just create an empty mesh with 0 faces, 0 edges, and 0 vertices. In other words, no edges, no faces, no vertices. Then we proceed to read from standard input a mesh in OFF format. So we're going to read from C in, and the result is going to get stored into our mesh object. So we read our mesh in, and we check to make sure it didn't fail. If it fails, we print an error message and exit with an exit status of 1. Otherwise, we continue along. And the next thing we do is we determine the mesh type. In other words, what type of faces are in the mesh? Are they all triangle faces, all quadrilateral faces, or is it a more general type of mesh? So to do this, we use the isPureTriangle member function of the polyhedron class. And this basically returns a true or false result. If all of the faces are triangles, it returns true. Otherwise, it returns false. So if it is true, then it means we're dealing with a triangle mesh, so we remember the fact that the mesh is a triangle mesh. Otherwise, we check this, we call the isPureQuad member function to test if all of the faces in the mesh are quadrilaterals, and this function returns true if they are. So if they are, we set this string that we're initializing to quad to indicate that faces are all quadrilateral. Otherwise, we indicate that this string called mesh type is general, just meaning that it's not a quadrilateral mesh or a triangle mesh. It's something a little bit more general. Then we proceed on next to loop over all of the vertices in the mesh, and we're going to compute some statistics that relate to the vertices. In particular, we're going to compute the minimum, maximum, and average valences of the vertices in the mesh. So to begin with, we initialize a running sum of all the valences to 0, and we initialize a minimum and maximum valence value to -1. -1 is just a special value. We know the valence can never be negative, so it's a special value just to say that these values, min valence and max valence, haven't actually been set yet. Then we proceed to loop over each vertex in the mesh with this for loop here. So we're using a vertex const iterator, which is an iterator that allows us to iterate over vertices in the mesh. And because we want our code to be const correct, because in this loop we're never going to use the variable vertex iter, this vertex iterator, we'll never use it to actually modify the vertex that it refers to. Therefore, we want to make sure our code is, in the interest of const correctness, we want to use a const iterator to indicate that we're not going to be modifying what the iterator refers to. And then we initialize it to the very first vertex in the mesh, which is returned by vertices begin. Vertices begin returns an iterator which refers to the very first vertex in the mesh. Then we loop as long as the vertex iterator is not equal to vertices end, where vertices end corresponds to one past the last vertex in the mesh. And each time through the loop we increment our iterator, so we'll step through all the vertices in the mesh. Then inside the loop what we do is we take our vertex iterator and we dereference it. When we dereference it, we're going to get a vertex, and then we call the degree member function for this vertex, which gives us the valence of the vertex, and then we remember the valence of the vertex by assigning to this variable called valence. Then we update the minimum and maximum valence values based on the valence of the vertex that we just visited, bearing in mind that the magical value of a negative valence means that we haven't actually set the minimum valence variable yet because it was initialized to -1, and also keeping in mind that max valence being negative also corresponds to max valence not actually really being set yet. Then we increase our running tally of the valences of all the vertices so we can calculate the average valence in a moment. And then after we exit the loop, the very first thing we do is we calculate the average valence, just taking the sum that we computed and dividing by the number of vertices in the mesh. Then we proceed on to another big loop, and in this loop essentially what we're doing is we're checking for non-planar faces and also computing some statistics related to faces, like the minimum degree and maximum degree of faces and the average number of sides to a face, the average degree of faces. So we start out by doing a loop over each of the faces in the mesh. Again, faces are called facets in CGAL. Facet is the more technically geometric correct term from a geometry point of view, but often we just call them faces. And in this particular loop, the iterator we use, we want to use a const iterator because this iterator variable, face iter, is not going to be used anywhere inside the loop in order to modify the face that the iterator refers to. So in the interest of const correctness, we want to use a const iterator. And we're going to iterate from facets begin, which is an iterator which refers to the very first face in the mesh. And we're going to keep looping as long as our iterator variable face iter is not equal to facets end, which is one past the last face in the mesh. And each time through the loop we increment our iterator, which is going to step through each of the faces in the mesh. Then inside the loop, the first thing we do, we take our face iterator, we dereference it, which gives us a face, and then we call facet degree for that face, which tells us how many sides the face has. The degree of the face is just the number of sides that the polygon face has. And then inside this loop, one of the things we're trying to calculate is how many non-planar faces there are. The only way you can have a non-planar face is that there has to be at least 4 vertices, because any 3 points in space are automatically going to be coplanar. You have to have at least 4 points before you have the possibility that the 4 points might not be planar. So in the case that the degree is greater or equal to 4, we have to worry about computing whether or not the face is planar or not. Otherwise, we don't have to do any computation for this. So supposing that the degree is greater than 4 and we have the possibility that the face might not be planar, the first thing we're going to do is we're going to determine the first 3 vertices in the face. We're just going to step around the vertices of the face and extract out the first 3 vertices. And then what we'll do is for each of the remaining vertices in the face, because there's more than 4 of them if we're going into the body of the if statement, for each of the remaining vertices, we'll check to see if each remaining vertex is coplanar with the first 3. And if this is true for every remaining vertex, this would mean that the face is planar. Otherwise, the face is non-planar. So we need to get the first vertex of the face. So we use a half-edge around facet circulator And in particular, we're going to use a const circulator in the interest of const correctness, because we're not going to use this circulator to refer to the things that the circulator refers to. So therefore, we want to use a const circulator, just like a const iterator, a similar sort of idea. And we're going to initialize this circulator to what's returned by the facet begin member function of a face. When we dereference the face iterator, we're going to get a face, and then we're calling facet begin for this face, which gives us a half edge around facet circulator for the face. So as we circulate around, we're going to be circulating around the half edges that are incident on this face. So what we want to do next is we want to record the vertex positions for each of the first 3 vertices of the face. So we take our circulator that's circulating around the half edges that are incident on the face, and then we dereference it, which gives us a half edge, and then for this half edge we call the vertex member function, which gives us the vertex at the terminal end of the half edge, in other words the incident vertex. And then for that vertex we call the point member function to get the coordinates, the actual point that's associated with that vertex. And then we save this thing, or we save a reference to this thing called v0. So v0 is a reference to the coordinate of the first vertex of the face. And then we step our circulator along to go to the next incident half edge for the face. And then we do a similar thing again. We take our circulator, we dereference it, which gives us a half edge, and then for this half edge we call a vertex member function, which gives us the corresponding vertex, in other words the incident vertex, the one at the terminal end of the half edge. And then we call the point member function to get the coordinates of that vertex. And we save this using a reference called v1, and then we step to the next vertex, and we do a similar thing again, and basically assign to the reference v2 the coordinates of the third vertex around the face. And then what we're going to do in the remaining loop that comes below here, in this loop here, is we're going to check each of the remaining faces, each of the remaining vertices. There must be more than 3 of them, because the if condition that we're inside of is if the degree is greater or equal to 4, so there has to be at least 4. So we're going to loop for each of the remaining vertices and check to make sure each remaining vertex is coplanar with the first 3 that we've saved up above here, v0, v1, v2. So we extract out the next vertex in the face. So we take our half edge circulator, we dereference to get a half edge, then we call the vertex member for that half edge, which gives us a vertex, and then for that vertex we call the point member function, which gives us the coordinate of that vertex, and we save this into this reference v, and then we increment our half edge circulator so it will go to the next incident half edge on the face. And then the next thing we do is we check for coplanarness of the 4 points. So we check to see if the first 3 points, v0, v1, v2, are coplanar with the 4th point that we've just extracted now. And if this is not true, then this means that we found a face that's not coplanar. Did I say that right? Yes, not coplanar. So we increment the count of the number of non-planar faces, and then we just print out a message saying that we found a face which is non-planar. We print 4 of the vertices that participate in the non-coplanarness. And then we break out of this loop, because we don't need to continue looping in the case that we found at least 4 vertices that are not coplanar. And then we keep looping. We hit the bottom of this loop here. We keep looping, basically going back up to the top up here, looping over each of the remaining faces in the mesh. And as we're looping over each of the faces in the mesh, we also update the minimum degree of the faces that we're encountering. In other words, the number of sides for the face is the degree. And we update the maximum degree, and we update our running sum of all the degrees of all the faces. And then finally we've iterated over all the faces, and we hit the bottom of the loop where we're iterating over all the faces, and then we'll kick out of the loop after we've iterated over all the faces. And the next thing we do is we compute the mean degree, which is simply the sum that we computed divided by the number of faces in the mesh. And proceeding on, the last thing that we need to do is we need to call the member function normalized border for the mesh. The reason for this is that we're going to use a few member functions in the messages that we're printing below in this very long print statement here. A few of the functions that we're going to call here, in order for them to be well defined and give us a value that's actually meaningful, in particular the size of border edges function in order for this to give a meaningful result, the border must be normalized. So we have to make sure that the border of the mesh is normalized by calling normalized border here, and then because of this, we know that sides of border edges will actually do the right thing. If the mesh isn't normalized and you call this function, the behavior is undefined. You don't know exactly what it's going to do. So after we normalize the border, then we just print this long message out that's saying what's the mesh type and what's the number of vertices and so on, all the different quantities that we've computed or extracted out of the mesh. And that's basically the whole program. The end of the main function is right here. Another simple example of a program utilizing the CGAL library is the meshSubdivide program. This program performs subdivision on a polygon mesh in order to produce a new refined mesh. To begin, the program reads a polygon mesh from standard input in OFF format, in other words, object file format. Then the mesh is refined by applying the specified number of iterations of the given subdivision method. And then lastly, the refined mesh is written to standard output in OFF format. And this program supports several subdivision schemes, including Loop, Catmull-Clark, Do-Sabin, and Cobalt Root 3. Now I'm going to give a walkthrough of the source code for the meshSubdivide program. This program consists of a single source code file called meshSubdivide.cpp. And if we start out near the beginning of the file, we have a bunch of include directives. The first two are not very interesting because these are just for the standard library. The next four are interesting because these are actually header files for CGAL. So the first header file here is for specifying or getting the declarations and definitions related to the particular geometry kernel we're going to use, which is the Cartesian kernel that shows up down here. Subdivision method 3 is used in order to obtain the subdivision functionality, declarations and definitions related to that. Polyhedron 3 is for the polyhedron 3 class, and polyhedron IO stream is for doing IO with polyhedron 3 type. So you can basically read a polygon mesh in from a stream and write a polygon mesh out to a stream in, for example, OFF format. Then the next part of the program, we introduce a few type aliases just to shorten some of the names of types we need to use in our program. So we introduce a real type, which is just an alias for double. And then we introduce the actual kernel that we want to use in our program, which is called a type name called kernel. And this is alias to the CGAL Cartesian geometry kernel. And we're plugging in as a template parameter the type real. So this parameter here corresponds to the type that's used to represent coordinates in this geometry kernel. So we're going to be using real coordinates, which are double coordinates. So the coordinates will be represented as doubles. And then we introduce a type name called polyhedron, which is just an alias for the polyhedron 3 type that we're going to be using from CGAL, which is polyhedron 3 with our particular geometry kernel plugged in. Then if we proceed on to the main function, the very first thing we do in the main function is check to make sure that the program's being used correctly. There's a number of command line options that need to be specified. You need to specify the particular subdivision method that you want to use, indicated by a string, and how many levels of subdivision you want to apply. So the very first thing we do is check and make sure that these pieces of information we need have been supplied. If they haven't been, we print out some messages to standard output just saying that the user is not using the program correctly, and we exit with an exit status of 2. But assuming everything is okay and the command line is fine, then we proceed on to actually do the real work of the program. So the first thing that we do is we extract out the particular subdivision method name that's specified as a string on the command line, and we assign this to a string called method. Then we take the number of subdivision levels, which is specified on the command line as argv2, we convert it to an integer value and then assign this to num levels. So num levels is the number of levels of subdivision we want to apply. Then we create a polygon mesh. It has the type polyhedron, so mesh is our polygon mesh. And it's default constructed, so it has no faces, no edges, no vertices. It's just empty initially. Then we read from standard input a mesh in OFF format, and we're careful to check to make sure it succeeded. If it failed, then we print an error message to standard error and exit with the exit status of 1. Otherwise, we proceed on to actually subdivide the mesh. So we check to see, first of all, was the method that was specified for the subdivision method loop subdivision. If it is, then we have to be careful to make sure that the mesh is a triangle mesh, because the OFF format that we're reading can in principle, have any type of polygon mesh in it. So we need to make sure that the mesh is a triangle mesh because loop subdivision can only handle triangle meshes. So to do this, we use the isPureTriangle member function of the polyhedron3 class, and it returns true or false. It returns true if the mesh has faces that are all triangles, otherwise it returns false. So if this returns false, meaning that the mesh isn't a triangle mesh, then we know that we can't actually handle this with loop subdivision, so we print an error message and exit with an exit status of 1. Otherwise, we go on and do loop subdivision, and we accomplish this by calling the loop subdivision function within CGAL, and it takes two parameters, the mesh that we want to subdivide and the number of iterations of subdivision to apply. And the mesh is modified in place. So after this function returns, this variable mesh will be modified to be the subdivided mesh. So if you actually wanted to keep the original mesh, you have to make a copy of it before you call this loop subdivision function, because it will replace this mesh with the subdivided mesh, and you'll lose the original mesh. If the case of the method wasn't loop subdivision, then we go on to this else if case here, and then we check to see, well, was it square root 3, the particular method, subdivision method that we were asked to use? If it is, we check to make sure that the mesh is a triangle mesh, because root 3 subdivision can only handle triangle meshes. If it's not a triangle mesh, then we simply print an error message and then exit with an exit status of 1. Otherwise, we continue on and we actually do the subdivision. So to do this, we call the square root 3 subdivision function. And again, it takes two parameters, the mesh that we want to subdivide and then how many iterations of subdivision we want to apply. And again, this function will modify this mesh. So after this function returns, mesh will now be the refined mesh that was produced by subdivision, and the original mesh will be lost. But maybe the mesh method, or the subdivision method that was specified, wasn't loop subdivision or square root 3, so we go on to this else if clause and we check to see, is it Catmull-Clark subdivision that was specified? Since Catmull-Clark subdivision can handle any type of mesh, we don't have to check, is it a triangle mesh or a quadrilateral mesh or anything like that. We just directly call Catmull-Clark subdivision function to perform Catmull-Clark subdivision. Again, it takes two parameters, the mesh to subdivide and the number of levels of subdivision, or number of iterations of subdivision to apply. Then we go on and check to see, well, maybe it was Deuce-Sabin subdivision. If it was, it turns out that this scheme can only be applied to quadrilateral meshes, so we check to make sure using the isPureQuad function that the mesh only has quadrilateral faces. This function, this member function here, returns true if all the faces are quadrilaterals, otherwise it returns false. So if the mesh isn't all quadrilateral faces, we simply print an error message because Deuce-Sabin subdivision can't handle this, and then return with an exit status of 1. Otherwise, we proceed on to actually do the subdivision, and again, it's a similar sort of situation as the previous subdivision functions. When we call Deuce-Sabin subdivision, we have two parameters. The first is the mesh we want to subdivide, and the second is the number of iterations of subdivision to apply. And again, the mesh is modified in place. So after the function returns, this mesh variable will be modified and replaced by the subdivided mesh, or refined mesh. And then if none of these cases were satisfied, in other words, the method was not any of the methods that was supported by this program, we just print an error message saying an invalid subdivision method was specified, and we exit with an exit status of 1. If things were successful, that we got this far, this means that we must have actually subdivided the mesh. So now we take our mesh and we write it to standard output, because the program writes its result to standard output, and this will output things in the OFF format. And just to be, perfectly correct, we check to make sure that nothing went wrong in the output operation. If something did, then we return with an exit status of 1. Otherwise, we exit with an exit status of 0, which normally means success. Usually 0 means success. A non-zero value means some kind of error occurred. And that's basically the whole program.